Today is going to be the last talk of the series, and I'll try to explain some ideas behind proof of this ultra-strong popularity lemma of the loss and security.
That's very good.
Yeah, and after that, I will try to explain the ideas behind the proof that perhaps we can find a recent dimension have the additional property. It's not very true. I mean, a better way to say it is, I mean, every graph of part of the dimension has a polynomial size clique or independent set. Right. So I think we will halfway through the proof of this and prove that I was going to present the proof by Hopstock and Sook. Okay. And last time we discussed the proof of this lemma, right? Which is the English version of Hausser's backing lemma. Right. So now, how to use this lemma to prove the Lubas-Security theorem? Right. So the idea here is pretty simple. So there's going to be some parameters that we're going to fix. I mean, that we are actually going to choose later. The first parameter is Q, which is exactly the Q above, some number L, and at the end, it will turn out that these two numbers behave like polynomials in epsilon inverse. We'll just choose it now later. Okay. So here's the idea. So let's say we are now living in a very big post graph G, of course, with VC dimension and most D. And so now we want to use a lemma. And we have the symmetric difference there. And also the definition of VC dimension for a graph was by looking at the VC dimension of a set system or the family of the open neighborhood of the vertices. So I'm going to classify the vertices into several types depending on this symmetric difference. So I'm going to take a maximal sequence. The vertices, let me say V1, V2, V3, first they go from G, such that the symmetric difference of every of the neighborhoods of every two of them is at least the number of vertices in G, of course, divided by Q. Just take a maximal sequence. Okay. And since G has VC dimension at most G, we can infer from this lemma that there is at most some constant C depending on D times Q raised to the power of 2. Okay. So in other words, no matter how we choose such a sequence, you cannot choose too many of them. Okay. Now here we are. Now we classify the vertices of G depending on the balls surrounding these VIs. And why am I saying balls? Because symmetric difference is behaving like a metric in the graph, in the sense that the symmetry difference obeys the triangle inequality. So it's classified the vertices. So as you can see, so these balls together will cover all vertices of G. So this is V1, this is V2, V3, V3. The property here is for every V in G, there is an I such that the symmetric difference of the neighborhoods of V and VI is at most G divided by Q. And we have this property because of the maximality of the sequence. Okay. Right. So now just look at an arbitrary ball BI. Here we have two vertices U and B, right? And what's the distance between them? And as I said, they mean the symmetry difference obeys the triangle inequality. So of course, for every I, if U and B are in the same ball, and you say, yeah, so let me say this ball is A1, A2, A3, and then K. Then if U and B fall into the same AI, I mean here of course I mean the AIs don't form a partition of I mean don't necessarily form a partition of BG, but let's say if there are two vertices falling inside, falling into the same ball, then the symmetry difference has to be not too large. Okay. Yeah, so maybe so if you want to make these AI is a partition of BG, then maybe you can change AI to what the AI minus A1 union, A2 union, AI minus 1. Just for convenience. So again, we may assume these AIs are pairwise disjoint. Okay. All right. So now, yeah. So now we have these properties. Now we look at this partition. Okay. So I'm gonna put the vertices G in some order, such that they will look like, such that each AI now will look like a subinterval, or maybe a subsequence of the whole sequence. So this is the sequence of the vertices of G, such that each AI will be a subinterval. So here we are in A1, and then this is A2, and A3, 1, 2, 3, 8, and then okay. Okay. So for now, I mean we have I mean we don't have any information about the size of the AIs, right? I mean we only know that they form a partition of BG, and then they satisfy certain nice metric-like properties. Now I'm going to try to partition this sequence into subsequence, into more subsequences, so that they will form a good equipartition of vision. What do I do? Now I'm just gonna partition, equipartition this sequence arbitrarily into about L subsequences. So here we are. Let's kind of look at, yes, so let's kind of look at this, and each such subsequence has length or size. Just to make things more rigorous, the ceiling or the floor of G over L. Okay, so far so good. So now we have. So let me say these subsequences are B1, B2 to BL. Does that make sense? Okay. So now let me say the VI is good. Here's the VI, not the. Let me say the. Yeah. The R is good if there is I such that VR lies completely in the ball VI. So the lies completely in AI for positive I. Okay. And of course, it is bad if it is not good. Bad if not good. So here, it is bad if it's lying between. If it is bad if it intersects two consecutive balls in a picture. Right. So number of bad boys, bad PR is from the utmost K. Right. So we have very few bad boys in the picture. Yeah. So the point of this sort of partition and then good and bad business is because we want to minimize the number of VRs such that we don't know. VRs with the scenario that we don't know how the vertices inside VR are behaving relative to each other. If VR is good, then we know that the symmetric difference of the neighborhoods of every two vertices in VR are going to be uniformly bounded. Right. So that's the idea. Right. So now all what's left to do is for us to estimate, the number of non-epsilon pure pairs. So now want to estimate number of non-epsilon pure pairs. The R is very when we say the RBS where RNS, RS are distinct and in the index FL. Okay, so these fall into two categories, right? The first is one of VRBS is fat. So this one of VRBS is fat. And the other kind is post-acute. Right. So the number of the first kind is, of course, most. How many of them are K times L? Right, because you have at most K bad VIs. So it remains to estimate the number of good pairs. So what do I do? So here's the picture. So this is VR, this is VS, and we know that they are good, right? Which means each of them lies completely within some block KI or J, and at the same time they are not epsilon pure, which means the number of edges between them, the number of edges between VR and VS is at least epsilon times VR times VS, and at most 1 minus epsilon VR times VS. Right, that's the definition. Okay. So yeah, so intuitively, right? The number of edges is middling. So intuitively, we would expect either a decent number of vertices in VR have the property that each of them has a decent number of neighbors and non-neighbors in VS, or there are a decent number of vertices in VS with the same property, but now with respect to VR, because the number of edges is not too small and not too large. So intuition. Either let me say decent number of vertices in VR, decent number of neighbors, and number of non-neighbors in VS, or vice versa. Right. So that's a probability the intuition. And here, so here to formalize this, we have a small claim, which can be done very easily. I mean, as long as you figure out the trick. So the target of this claim is to count the pairs of edges and non-edges between VR and VS that look like this or like this. So we want to count the pairs of edge, the pairs of the form edge, non-edge between VR and VS, such that they share a common endpoint. So, let me see. Sorry, sometimes I run out of quotations. So let M be number of pairs of the form E and E prime, where E is an edge between VR and VS, and E prime is not an edge between VR and VS, and we have a common endpoint. Okay. And then M is at least epsilon times 1 minus epsilon. I think times, let me say, G divided by L ceiling, raised to the power 3. Yeah, but this, I mean, this is actually VI, so you have VR times VS times minimum of VR and VS. Actually, what it says. Okay, so the trick here is pretty simple. I'm only going to sketch the proof, and I think I'll let you figure out what to do. So, to get the trick. So again, this is VR and this is VS. So you're going to pick two vertices uniformly at random with repetition from VR, and at the same time, two vertices uniformly at random with repetition from VS. So the two of them and X, Y, Z. X, Y, Z, T. Okay, so X, Y uniformly random, two uniformly random vertices from VR chosen with repetition, and the same for ZT, same for ZT inside VS. So the observation here is if X, Z are adjacent, and if Y, T are non-adjacent, right? Then either X, Z, Y, Z becomes a targeted pair, or Y, Z, Y, T is a targeted pair, right? So for example, if Y and Z are not adjacent, then X, Z, Y, Z are what we want to count. At the same time, if Y, Z are adjacent, then Y, Z, Y, T are formed pair that we wish. Okay. So over what's left to is to estimate the probability that Z is in B and B and YT is not in B. Right? Yeah, and it is equal to the probability that XZ in G YZ is not in B. First, the probability that YZ is in B and YT is not in B. Right. So yeah, and this quantity, right, is exactly equal to the number of edges times the number of non-edges, all divided by so VR squared, VS squared, right? And you know the number of edges is between, I mean the density of edges is between epsilon and 1 minus epsilon, so the concavity is at least epsilon times 1 minus epsilon. Okay. So now, yeah, so this quantity basically is actually
I mean, I think I know what you were trying to say, but this equality is strange, right?
Oh yeah, I think I
Yeah.
need more. Yeah, so yeah,
Conditional
yeah. So yeah, thank you. Yeah, I mean there should be some more here. Conditional problems there. So I got a bit too fast. Yeah, but anyway, so now you get the idea, right? This is actually counting the number of pairs E prime above with the fact that the common endpoint is in DS, right? That's for the first term. The second term is counting the number of I mean the number of pairs E prime such that the common endpoint is in DR. Right, now you get condition proof. So right. So yeah, so this thing is a way to count, I mean, the number of these pairs, right? I mean, the number of let me say the number of behaving pairs only, non-behaving pairs. So let me say E prime, which is probably like for the non-behaving pairs, E prime edges. Okay. Yeah. So we know this, and now we try to apply this claim, right, for all of the math pairs. Sorry, for all of the non-epsilon pure pairs VRVS, with the property that VRVS are good. So yeah, so if I let here, let me list P the number of non-epsilon pure pairs. VS where VS are good, right? Then and from this lemma, number of non-behaving pairs E prime between good pairs. Good pairs, right? Is at least what is that? Epsilon times one over T times epsilon minus epsilon E now. Right? So number of non-behaving pairs E prime between good pairs VRVS. So now we have we already have a lower bound. So now we want to estimate a good upper bound. And what do we do? Right, so now going back to okay, so going back to this property, right? So every good subset, I mean, belongs to some ball. So symmetry difference between two is the symmetric difference between two arbitrary vertices from the same set VR or VS is going to be small. So the number of non-behaving pairs E and E prime with E hat E prime subset. Yeah, so the unique vertex, which is the common endpoint of E and E prime, is in the number of such pair for each arc. This is going to be at most with E. With E union E prime. It's not true. E set minus E prime and E prime set minus E. So the two private endpoints of E and E prime are in VR. Yeah, just a better way of saying it. So two vertices in VR, and now you want to count the number of vertices outside that are adjacent to one of them and not adjacent to the other. But it's gonna be at most. Every pair, so it's gonna be PR plus 2 times 2 E divided by Q. Okay. So from this, we deduce that so this is for every R. So for each R, which are what we are is with. So now the number of total this for some we are good. This is going to be now at most L times. So this is let me say at most E over L square divided by 2 times 3 Q. This is L times G over L square times E over Q. Okay, so now we have a lower bound and an upper bound. Right? Now, P epsilon epsilon. Now, okay, is most now times right. So here we may assume that as I said, so later we will see that L is actually some power of epsilon. So we may assume that just to avoid some technicalities, we may assume that the number of vertices of G is much bigger than L. Let me say. Then I have to see that the ceiling function has to be at most half of the floor function. So almost twice the floor function. So I know many people in the area. I mean, want to get. I mean, just like to write things without floors and ceilings. But I think I'm trying to be rigorous here. So sorry about that. So okay, so now we have that it, right? On G. Now we can cancel. I mean, these two. So what we have is 1/8 epsilon 1 minus epsilon times G divided by L is most L times Q. Okay, it's good. So this is equivalent to the fact that P is at most L squared 8 times L squared divided by Q epsilon 1 minus epsilon, right? And we know that 1 minus epsilon. So I think I'm assuming that epsilon is from 0 to 1/2. So this is at least 1/2. And so this is almost 16 L squared divided by Q times epsilon.
Can you lower a little?
Oh,
Now I see.
okay. Okay, good. So where to erase? All right, so now we're back to this picture. The two categories, so now we have it. We have got a good upper bound on the second kind, and so here is at most 16 L squared divided by Q times epsilon. Right, and I'll just take the summation of most of them. So A times L plus 16 L squared divided by Q epsilon. And as I said, A is from the beginning, A is at most, I think I erase it. So at most CD times Q to the 2D times L plus 16L squared divided by Q epsilon. And now, because we want to show that the number of non-epsilon pure pairs is at most an epsilon fraction of all the pairs, right? So we want to now, all what's left to do is to choose Q and L, right? Such that this is at most epsilon times L choose 2. Right? And so it's should not be too hard because okay, so instead of saying L choose 2, let me say L squared over 4. Okay, because this is going to be almost L choose 2 times epsilon. Right, but this is not too hard because this inequality is equivalent to CD times Q to the 2D divided by L epsilon plus 1 Q epsilon is at minus 1 over 4. So now we're supposed to choose, I think we can choose Q to be it over epsilon, right? Put ceiling if you want to. Right, so 8 over epsilon, and then choose L such that this is also almost 1/8. So L is put ceiling here. CD CD times Q to the 2D times epsilon increase. Right. So now this is some power of epsilon. And this Q is linear in epsilon, and this is linear. This is okay, some power of epsilon. Right. So now then choose a accordingly. Any question?
Yeah, it might be a still depends also.
Yeah.
It is usually usually once we have a regular partition, then it's very convenient to consider its reduced graph
Mhm.
because its reduced graph having inherits the many useful properties of the host graph. So my question is it true that the reduced graph of this bounded equal dimension graph also having a bounded dimension?
That's a very good question.
Maybe I think it
Whether
with the embedded.
So what do you mean by reduced graph?
I mean,
Just look at the epsilon.
yeah, epsilon dense. I mean, 1 minus epsilon dense, then we adding a
An edge.
edge, and epsilon poor, then we do not add an edge.
So what about the pairs that not epsilon pure? What do you want to define the graph?
Usually in that case, we don't adding non edge. So,
Oh.
Maybe red ends.
Maybe also that's a good question. I don't know.
maybe we could consider embedding. Yeah, with the embedding and diagnosing things.
Yeah, I think so but I guess it depends on the way that you handle the non-epsilon pure pairs and then how you define them. Because I mean this is about induced graphs, so we gotta be careful a little bit when we handle the irregular pairs. Yeah, but that's a good question. I never thought of that. Right, so I think we're gonna have a break for 5 minutes, and then we can Erdős Hajnal. Yeah, so we continue with this PC dimension business, and so I have just written now a corollary of the probably straightforward corollary of the ultra strong regularity lemma, which would be useful in the proof of Erdős-Hajnal conjecture for graphs of the PC dimension. And here, as you can see, again, if G has valid VC dimension, then you can find this subset of G with size pretty decent, polynomial size. So some power of epsilon, but the power depends on the VC dimension and time G. Good. Such that every pair in the sequence so such that every pair are strongly epsilon pure. So now so it's strongly epsilon pure means they are epsilon sparse or epsilon dense to each other. So the definition of epsilon pure was by counting edges between the two sides, right? But now we have a little bit stronger condition, which is strongly, and strongly means now the mass degree from one side to the other. Means either the mass degree from one side to the other is small, or the mean degree from one side to the other is small. Sort of uniformly for both sides. So yeah, because I mean later when we go into proof of Erdős-Hajnal, then we'll need this mass or mean degree condition, and the density condition alone by counting edges is not going to be enough. Yeah, but there's just some technicalities, and the proof is it's not so hard. You start with the ultra strong regularity partition, but now with density parameter epsilon cube. All right, and now as usual, you use the round to get a sequence of subsets. Possibly, if you want to be K such that every two of them are epsilon pure to each other. And now you do some cleanup things by removing the vertices from each BI with the wrong adjacency to one of the other parts in the sequence. So This is supposed to be an exercise if you want to try. Okay, so now go to Erdős-Hajnal for graphs of multiplicity dimension.
So how large is K?
K is about epsilon inverse. Yeah. Yeah, so we choose K to be epsilon inverse about that, so that the cleanup business can be done. Right, so the last result today, we want to the last result this series of talk is going to be written without the three of us. Let me say it should be populist. Yeah, so again for FD, this one, let's say, let's see star such that EC dimension G is a D, then G has a quick independent set size at least G raised to the power of C. So so before that, this was conjectured independently by two groups of researchers, conjectured by Oscar Stuck, which is actually a team that came up with the proof that I just presented, or just from regularity lemma, actually in the same paper, and also this. So this is a group in extremal and geometric combinatorics, and we have a group in model theory. In the top, starting from so why model theory people care about this is because of the definition of VC dimension. If you are familiar a bit with VC dimension, then you know bounded VC dimension means NIP. I'm not going to go into that today because I am not a model theorist. Okay, so and also in the same paper here, Oscar also got a pretty nice bound, which was 2 to log G raised to the power of 1 minus the order 1. Here, the little order 1 term depends on this. So the constant depending on the VC dimension is hidden in the little 1 term. So, so in other words, so what Fobbs, Park and Suk got was the near Erdős-Hajnal property. I mean, the near Erdős-Hajnal result for graphs about the VC dimension. And what they did was roughly by applying directly this corollary. So, so to explain this, I mean, in detail, it's going to be messy because you have to do with calculations. But the idea here is, so you have a sequence of subsets. Right. The number of the subsets is going to be roughly some power of epsilon inverse. That's the first thing. And the size of each subset is also roughly some power epsilon times G. Now, and you know, and you also know that, I mean, every pair among these subsets are strongly epsilon sparse or epsilon, are strongly epsilon pure. Yeah. So if you go into the usually if you do a very standard trick in the regularity world, which is considered the reduced graph of this sequence of subsets, then you're going to see that you're going to get again a graph, an auxiliary graph with bounded VC dimension, but now with roughly this many vertices, and so in other words, you're going to get a smaller graph, which is auxiliary graph, also about the VC dimension, and then it is very natural to apply induction. But the point here is you have the reduced graph, these blobs. and you know that it has bounded BC dimension, but you don't know anything more about its structure. So that's why this idea lead Oxford and Patterson suit to this bound, but not the full Erdős-Hajnal bound. So long story short, as long as we have this, we should be able to do something to say more about the structure of the reduced graph. The reduced graph should be more restricted in order for us to gain a clique or independent set of polynomial size. Okay. Right. So the idea. So one of the key ideas behind the recent work on Erdős-Hajnal is just to get full Erdős-Hajnal results. So for example, this BC dimension result and also the D5 result, the infinitely many prime graph results, and holes and anti-holes and so on, is the idea of iterative sparsification. So iterative okay. So what is it? So if you remember in the maybe the first two talks, we discussed Rödl's theorem and maybe the polynomial Rödl property, and we also discussed that Rödl's theorem is good, but if you only know about the current rational bounds for any general graph, then in practice, perhaps it is only going to be good if you want to aim for constant density parameter, right? So Rödl's theorem is like you start with a graph with a forbidden induced graph. Now you input a density parameter epsilon. Epsilon is density parameter. Right, and plus, and as I said, the host graph is missing some induced graph. Let me say H. Right, so H is free, and now the output is going to be some delta depending on H and epsilon. Right, such that you can shrink the host graph by a factor of delta, such that the induced graph that you get is going to be epsilon sparse or epsilon dense, right? So the point here is the dependence of delta on epsilon, right? If you use the regularity lemma, it's going to be tau type, and if you follow the recent progress on it, then delta is sort of quasi polynomial in epsilon, but still not quite polynomial. So yeah, so for application, if you want to get a full Erdős-Hajnal result, then perhaps the best way to do, if you want to apply Rödl's theorem, is to start with epsilon being some constant. And here, in particular, epsilon is better to be a constant depending on H. So to start with epsilon with some supposedly very small constant, depending on H. And if you do that, then delta is also going to be a constant depending on H. Okay. So, in other words, that's going to be T, right? Depending on H, such that delta is epsilon. Okay. Yeah. So now look at this induced graph. We know that it is pretty sparse, pretty dense. Yeah, but it is not as sparse or as dense as we want, right? Because it's just a constant. I mean, the density parameter is just a constant. I mean, so for example, the mass degree is at most maybe 10 to the minus 10 times the size of times the number of vertices of this induced graph. And so it is. So there's not much to say about large clique or independent set inside this induced graph. So now here's the idea. So let's assume in a very nice world, we can somehow shrink this induced graph a little bit further. Shrink it a little bit further. To get what? To get a smaller induced subgraph, also very dense or very sparse, but now with much better density parameter. And the payoff, the trade-off is with the trade-off, which is the shrinkage factor, is comparable to the new density parameter. So finally, string induced subgraph by a decent or good factor to the induced subgraph with much better density parameter. Right. So now we're in the second induced subgraph. So now let's assume that we can keep doing this continuously, right? Do this indefinitely, and which means we can keep shrinking this induced subgraphs. These induced subgraphs shrink, and each time we are not getting by much. The amount that we play is going to be comparable to the new density parameter every time, and then at the end, you're going to hope that at some point, the induced subgraph, even though very small, would also at the same time be super sparse or super dense, so that we can get a large clique or independent set. So here is the lemma. So we have several input variables. So first, we have C is some constant from 0 to 1. Saying C will not be good enough. So and X and Y are two variables. So Y will be our floating density parameter, and X is going to be our target density parameter. Okay. Less than 1, say, and so T is this 1, and the number is 2. So we have a graph G satisfying these two conditions. So first, there exists an induced subgraph of G, okay, C sparse or C dense, and with at least C to the P of G vertices. Yeah, so at this point, this is just basically what Rödl's theorem gives you, right? And the second condition is for every induced subgraph f of G, with at least how many vertices? No, sorry, not how many vertices. For every induced subgraph of G, that is Y sparse or Y dense. There exists an induced subgraph f prime of F that is Y to the A sparse or Y to the A dense, and also satisfies the number of vertices at F prime is at least Y to the 2t times number of vertices at F. Okay, so far, we have said nothing about X. Now we're going to have the conclusion. I'm not doing it the best way because the lemma has to be written into blackboards. Yeah, in this lemma, conclusion is there is an induced graph G x bar or x times. And with at least x to the 280 times G versus. Right. So the first condition, so here in this lemma, the first condition is just merely what Rödl's theorem gives you. Right? If you start from C and T being constants, then being constants depending on the graph H. And the second condition is exactly a formal manifestation of the idea above. That you can keep shrinking the induced subgraph, right? To get one with much better density parameter, and we are not shrinking by much. So the proof of this is not too hard. In fact, you can actually do it in two ways. So for example, you can do it by just keep getting induced subgraphs like in this picture, or you can do it this way. So this is proof. Yeah, so now I want to let Z from X to A or this X to A and Y would be minimal such that there is an induced parameter J F F of G with at least Z to B to the 2T, Z to the AT, maybe Z to the 2T times Z times G, and F is Z sparse or Z down. Okay, and this Z certainly exists because you can just put Z to be Y, right? And use the first two conditions. Okay, so not Y, but sorry, so Y is X to A to C. Yeah, so you can just put Z to be C, and now you apply the first condition. Okay, so this Z certainly exists, and because we are living in the finite graph G, there is some minimal Z with this property. Okay, now I claim. So the claim here is Z has to be at most X. Okay.
Do you want square root of C over there instead of the C?
Square root of C. So where?
Oh no, I see. No, I was thinking about. Wait, so in the first condition, you have a C sparse graph or C dense graph with the C to the T G vertices, right?
Yes.
Here you have a G to the 2T times G vertices. I don't know why. So you have 2T here.
So you have C to the T, obviously is at least C to the 2T.
Oh,
Yeah.
I see. It's smaller than one.
Yeah.
All right.
Any question? Yeah, yeah, and I think. Any question?
Is there no relation between C and Y?
No. So C, so yeah, so in practice, C is supposed to be some constant depending on the graph H that we are trying to exclude, and Y is supposed to be a floating density parameter. So we're gonna decrease Y continuously starting from C to some target density parameter, and in this case, it is X. And in practice, if you want to get full addition result, then you can just plug. I mean, you can just put X to be some small power of G inverse. That's the idea. And any other question? So, all right. So my claim is now Z is almost X. And suppose not. Right. So Z is bigger than X. So now I can apply the second condition with Y being Z. Right. So my second condition. Right. So that's going to be the user graph F prime. F with the property that F prime is at least Z to the 2t times F. Okay, Z to the 2t times F. Oh no, sorry. This is not Y to the 2t. Sorry, this is Y to the 8. Yeah, so Y Z to the 8 times F, and at least Z to the 2t plus 8 times G. And because I is at least 2, we'll say this is at least Z to the 2 80 times G. Okay. So again, F prime is not too small. And at the same time, F prime is Y to the A plus or Y to the A gas. Right? This is what the second condition would give you. Makes sense? So again, so in other words, if the density parameter is not too small, then we can string the induced graph F a little bit more. Okay. Oh, this one Z. Okay. Yeah, so for Y. So yeah. Thank you. Yeah. So so setting here is you're absolutely right. Sorry about that. Yeah, so here is for every Y and X. Thank you. Yeah, sorry for a bit quick. Any other question? Hopefully. So we try to pass to a better induced graph here. Now, this would give a contradiction, right? Because Z to the A is of course at least X to the A, right? And Z to the AT is raised to power 2t. So this violates humanity. So far, good. Any other question about this lemma? I mean, the numbers look. Actually, the exponents look a bit magical, but perhaps in a more natural way to deduce this is just to get a sequence of induced graphs, and now you try to sum a geometric series into exponent. But I'm not going to do that. It's just going to be a bit messy. So yeah, but again, this is the lemma that rigorizes the idea of, and as you can see, everything is polynomial. So in practice, C and T are constant. depending on h, of course, and x is going to be g raised to some very small power, g to the minus tau or some very small. So it's C, A, and T. So A, C, T, and x is going to be some very, very small power of G inverse. And also depending on which positive. Is what we are supposed to do. Right, because the point here is if we are because when we reach the end of the process, x plus or extend with this many vertices, if we try to put x to be, this function of g, then you can apply Turan's theorem to extract a clique or independent set of polynomial size. Right. So now we go into the proof of this. So here is one thing that I want to emphasize. So remember yesterday we were talking about some sort of equivalent characterizations of perhaps the part of BCD mentioned, right, in terms of bi-induced copies and excluding a parted graph, a parted graph, and split graphs, and so on. And so for the rest of today, I'm not going to talk about BCD machine anymore, but instead I'm going to talk about bi-induced copies. So actually, this theorem is equivalent to or by graph, which exists C small such that if G doesn't bicontain H, and here by graph H with by partition we want to. If G doesn't bicontain H, then you have the simple theorem. So this is actually what we're going to prove. And the proof is going to be by induction on the number of vertices of H. So induction. So I think I have 15, 20 minutes left. I'll try to.
So in theorem, we should assume G is H3 for some H, right?
No, it doesn't bicontain H. It has no bi-induced copy of H. This is what we discussed yesterday.
In the theorem, we want to prove.
Yeah, but I mean G has found a BCD dimension if it doesn't bicontain some bigraph. That's what we discussed yesterday.
Yeah.
So that's what I'm trying to. I will stick with this statement. Is that clear?
Yeah, I mean, the theorem we want to prove is that if G has bounded this dimension and is induced H3 for some H.
No, it doesn't have to be induced H3 for. I mean,
It has nothing to do with the H3.
yeah, this theorem has to do with
Let
H3.
device found with the we already told this something.
Yeah. Any other question? Okay. Yeah, so now let us start the process. So here we have these things, right? I mean, about density and then trying to string into an induced graph and so on. So now, as usual, we would like to start from Rödl's theorem, as I said here, with some constant density parameter, shrinking the graph by a constant factor to get a constant dense or constant sparse induced graph. And then we would like to keep shrinking the induced graph in some way. Okay. And of course, we cannot expect this shrinking business to happen smoothly every time. And in fact, there is another condition that could give us the full Erdős-Hajnal result, which was first observed by Istvan Tomon. So first observed by Istvan Tomon. So this observation. The credit to Tomon here. That so assume for every induced subgraph f of g, assume that for every induced subgraph of g with f at least so now poly y. So from now on, y is going to be our floating density parameter. And f is y first or y dense. There is a sequence. A1, A2 to AL of subsets. F such that I is also this poly y times F conditional y and AI AJ are uniformly compete or uncompete to each other. Then mass of alpha G omega G is going to give this G to some small power. And of course, later we will try to plug in the number. So here uniformly compete or uncompete means so here it is in the subsets. Also, sorry, and also forget to say that L is also at least some power of Y inverse. So here we have a sequence of subsets, right? And with the property that either there is no edge between any two of them, or all edges are present between them. So no edges everywhere, or all edges everywhere between any two sets. Okay. And if this keeps happening for every induced graph f of g with these properties, then we are good to go. So this is a more restricted version of the observation of Tomon. And the proof of this is by induction. And so it's kind of similar to what we discussed about the probably discussed maybe 2 or 3 days ago about the Erdős-Hajnal bound. So we keep getting biggest co-graph inside these subsets, and now we're trying to combine all of them to get a bigger co-graph. So, yeah, but I'm not gonna give it the proof. Okay, so now let me discuss the idea. Right, so now let me assume we are living in a sparse induced graph G. Let me say that's F, and the induced graph is Y sparse. I mean, the Y dense scenario is, it's not going to be too different. Okay, so here we are, Y sparse, and the size is at least poly Y for G. Okay, so now I would like to apply this result this corollary to the induced graph F. And here F. Yeah, so I'm gonna get the sequence of subsets, right? Pairwise from the epsilon period of chart. Okay, but here I have to choose epsilon. So what am I going to choose? I will choose epsilon to be some huge power of y. So y raised to some power. We can. And later we'll see that this m is going to be roughly b cubed, where 1 over b is given by induction applied to h minus b. So here's the bar graph h, right? And here's some vertex b. Let me say this inside V1 in this V2. And V has a certain set of neighbors and a certain set of non-neighbors in V2. Okay. So by induction, as I said, if I try to remove V from H, right, then I can get some number C prime, which I will let it be 1 over B. So C prime. Okay. Okay, so far, nothing to talk about. So epsilon is going to be a huge power of the density parameter. So now here's a pretty common trick in graph theory. So you have a structure like this, and they could be pretty small, but not too small. Now, what you want to do is to try to look at how the rest of the graph attaches to this structure. And in this case, the kind of attachment that I want to look at is having a neighbor and a non-neighbor inside some particular block in this sequence. So let me say here I have B1, B2, 2, BK. And here is a vertex U outside, still in F, but outside of the blocks. So U is mixed on some BI. It has a neighbor and a non-neighbor in BI. Right. Right. So again, K here is epsilon inverse, which is y to the minus 1, which is huge. Right. All right. So now I ask, can this vertex U be mixed on too many of these blocks with K? And if it, and if it is, then what's going to happen? So let's say U is mixed on at least a y fraction of these blocks, BK. So let's suppose I can have, I see lots of blocks. Lots of blocks. There's B1, B2 to B, YK. Okay. So now it is, so U has a neighbor and a non-neighbor in each of the BI where I ranges from 1 to YK. Let's assume that. Okay, so now what can happen? I would like to look at the pattern graph of these blocks B1, B2 to BYK. Right? This has a pattern because of this strongly epsilon pure property. So look at the pattern graph. Of B1, B2, BYK. Let me say this pattern graph is J. And now I ask, is J going to bicontain H minus D? asked. So if J doesn't contain H minus B, then what? Then J is going to contain a large clique of independent set. Okay, then max of alpha J omega J is going to be at least J to the C prime, which is J to the 1 over B. Okay. So what does a big independent set in J translate back into this picture? You will get a sequence of, a subsequence of blobs which are pairwise strongly sparse to each other, right? Because that's the way we define the fucking graph, right? I mean, the two vertices representing two blobs have an edge if the two blobs that they represent are dense to each other, and vice versa. So in other words, a big independent set here will give you a sequence, a subsequence of subsets pairwise sparse to each other. Okay, and now the density parameter is huge, right? The sparseness parameter is epsilon, which is y to the m. So a very large power of y. And now have this sequence of subsets pairwise sparse to each other. If you try to combine all of them into one, then you're going to get an induced graph with density parameter roughly the number of these subsets. So take a union, right, of the blobs in the subsequence. So induce a graph that is roughly this amount. So that is J 1 minus J to the minus 1 over B sparse. The point here is every two of them are super sparse to each other. So now if we take the union, and because we do and because we don't know what's happening inside each block, the new density parameter is going to be roughly the inverse of the number of blocks that you started with. So it's going to be this one. And now if you try to compute it, because in J is yk, and we still a large power m with yk is 1 minus m, right? And if you choose m to be b cubed, for example, then this is still a huge power of y. So this is actually roughly y to the minus b, y to the b squared. And what about the size of this induced graph? It's going to be at least the size of any particular block that we have chosen, right? And the size is going to be epsilon raised to the power of m, and also epsilon raised to the power of big D, which is y to the mb. Okay. So which is y to the b cubed times d. So now if you look at this, then the shape is very similar to the shape in the iterative sparsification line over there. I'll let you do the numbers. Right. And there's the same situation arises if you see a big clique inside J. Now instead of sparse, you have dense. You have a sequence of blocks, many of them pairwise dense to each other. You combine all of them, and then you get a very dense induced graph. And now you move to the dense case. So I may assume that J does contain, if I may assume that J does contain H minus B. So here we are in this pattern graph J. Y contains H minus V. So what does it mean? That means now, so now I look at the blobs representing the copy of, the bi-induced copy of H minus V inside J. Right? And I can classify them into two. The left row is going to be those representing V1 minus V, and the right hand side is going to be those representing V2. So V1 minus V is V2. So here I have U. And now my job is to try to construct a bi-induced copy of H inside this picture. So what do? I'm going to start with embedding the vertices of V2 into these right-hand blobs. So for each neighbor V in V2, I'm going to pick a neighbor of U in this corresponding blob. Let me say this is W1, for example. And then I do the same for every block representing a neighbor of U on the right-hand side. W1, W2 to WR, for example. So now I have done with the neighbors of V. And I'm going to do the same for the non-neighbors of V in V2. So for each of the blobs representing the non-neighbors of U on the right-hand side, representing the non-neighbors of V on the right-hand side, I'm going to pick a non-neighbor of U in the corresponding block. And I can do that because U is mixed on all of them, right? That's what that's how we define U. Right? That's how we that's what we assume at the start about U. Okay. So now the point here is I don't care about what's happening between these vertices, right? Because we're trying to embed a bi-induced copy, and so we don't have to care about the edges or the non-edges between the vertices representing V2. Okay. So now I'm going to use the strongly sparse or dense hypothesis, right? I have the mass degree or mean degree condition, and they all respect the adjacencies of the vertices between V1 and V2, or the vertices in V1 and V2. So that means, so for example here, if I want to embed the vertex V prime in V1 into the left-hand side, I'm going to look at the block corresponding to V prime. Let me say that's VV prime. And now I'm going to get rid of the vertices in VV prime with the wrong adjacency to all of these embedded vertices. And I can do that because of the mass or the mean degree condition. So get rid of them. And now I still have lots of vertices here with the correct adjacency to all of them, to all of the embedded vertices on the right-hand side. And so I can pick one and let this vertex represent V prime. So W prime set, which has all the correct adjacency. Okay, and then I can keep doing so for all of the rest of V1. And so I can construct a bi-induced copy of H in this picture. Okay, well, so I'm a bit over time now, but let me just say, so now we assume node U outside is mixed on this YK. These 5K blobs over there. Right. So now we are in the sparse graph. And every vertex outside is mixed on very few of them. And we also have the sparsity condition. So now it is not hard to say that there has to be a block with the property that almost all of the people in the rest of the world are incomplete to it. Now you can keep going. Why? Because, and by almost all I mean, the quotient here is at least 1 minus some constant times y minus constant. Yeah, so I still have many vertices here. And what do I do next? I'm going to repeat the same procedure inside this huge part of F, and then I can keep going. And if I can keep going like this, and by looking at this expression, then I can do it for about y to the minus 1 times, which would lead me to this condition in the observation of Seymour. So here's about averaging viscosity. There's one block, which is incomplete, to about to at least 1 minus 2 media function of y and f versus. And now keep repeating the same procedure inside this part to get repeating this for y to the minus 1 times. And then that incomplete sequence as in common observation, which is defined. Of course, maybe there has to be something more to do with numbers, but yeah, but that's the main idea. I think I should stop it.